All right, so this is the first video to Module 4. So we're starting organic chemistry, and so we're going to be in organic chemistry for Module 4 and 5. I want to preface that this is going to be a tough couple of weeks. Organic chemistry, or it's commonly known as Orgo, is not easy. When I first saw the OWL assignment, it was 22 questions, and I thought some of them were really hard, so I removed some of them because I know that you guys already struggle to get the 16, 17 in. So I just want to preface that this is going to be a tough couple chapters, and that you're really going to need to put in the time for these couple chapters. So we're responsible for covering chapter 11, 12, and 13 this week. I haven't separated the videos based off chapters. I've more so regrouped them, just because I think it makes a little bit more sense. So my first video will be an introduction to organic. Second video will be properties and naming. And the third video will be reactions. So what is organic chemistry? So the term organic was first used in the 19th, 18th century because the compounds that they were studying were extracted from plants and animals, which they considered organized systems. So now the term organic, right, we don't normally associate organic with plants, animals, but rather the food industry has stole this term and kind of labeled it as food grown with or without pesticides or synthetic fertilizers. Well, what does organic chemistry refer to in today? Organic chemistry refers to carbon-containing compounds. Organic chemistry is centered all around carbons. Carbons are very important in organic chemistry. So, organic molecules contain carbon. So this molecule right here is an example of an organic molecule, where magnesium nitrate is considered inorganic just because it doesn't have carbon. Now, we are not going to talk about organic molecules or inorganic molecules like at all, but I just want to preface. And so some common properties of organic compounds is that they are covalent. They generally are weak when they try to join forces with each other. They are usually in gas or liquid states with low melting points. They're often flammable, not very soluble in water, not very good conductors of heat, and they're usually pretty slow in chemical reactions. So this understanding organic chemistry is a lot of understanding the structure of the molecule. And so, like we talked about, carbon is very popular and important in organic chemistry. But why is this? So, organic molecules usually contain long carbon chains. And so they use these carbons as backbones because carbon has the ability if you look at it's on the periodic table, it's a +4 or -4. It has 4 valence electrons, and therefore it has 4 places in which it can bond to other molecules. So this makes carbon very versatile. Makes it a great backbone. So here's another example here where carbon's used as a backbone. You see, when we add oxygen, oxygen only has the ability to form 2 bonds, as opposed to carbon having 4. Right, so this is why carbon is the backbone to all organic molecules. So like I said, understanding organic is a lot of just understanding how these molecules are structured and how they're depicted. And so we've talked already about molecular formulas. We've talked a little bit about structural formulas, right? So if I were to draw something like this, showing how each of the atoms are arranged. This is the structural formula, right? So I have 3 C's, 8 H's. But organic likes to make this simpler because they use carbon and hydrogen all the time. So they like to basically shorthand it, where every carbon is a point of a line. So if I were trying to depict this molecule, C3H8, I can just depict it with lines and points. Oops, one too many. Okay, so this C right here is represented by this point. This C right here is represented by this point. This C right here is represented by this point. Now, I could draw out the H's and show each H here. But, like I said, we like to be lazy in organic chemistry. We like to make things easier for ourselves. So we often imply the hydrogens. We know that carbon has 4 bonds. And so if it has 4 bonds, then there's an implied 3 hydrogens here. There's an implied 2 hydrogens here because 2 bonds are already used to connect to the other carbons. There's an implied 3 hydrogens here. So sometimes we're lazy, right? We draw these stick models. Sometimes we meet halfway with the other chemist and we say, okay, fine, we'll do a condensed formula in which we basically group each carbon atom and what's attached to it. So if I was to write this C3H8 as a condensed formula, I would write it as CH3, CH2, CH3. And so this depicts this first group, the CH2 depicts the second group, and the third group there. So these all mean the same thing. Let's do another example here. Let me draw a line because I'm going to run out of room. Okay, C5H12. So I need to make sure I have 5 carbons on my backbone. we know that carbon can form 3 or 4 bonds. So I'm going to go ahead and start filling in 4 bonds for each carbon by adding a hydrogen atom. I'm going to double check that this equals 12, but it should. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Great. So if I wanted to represent this in the stick model, I'd represent each carbon as the end of a line or a point. So 1, 2, 3, 4, 5. And I could connect them all. You don't have to do the dots, but sometimes I like to do that. I'm going to take away the dots real quick. 1, 2, 3, 4, 5. Yep. Okay. And so, like I said, there are implied hydrogens. There'd be 3 implied hydrogens here, 2 implied hydrogens here, 2 implied hydrogens here, 2 implied hydrogens there, and 3 implied hydrogens here. And so the condensed formula, we group it by carbons. So CH3 covers this group. CH2 covers this group. CH2, CH2, CH3. I know I'm running out of room there. Okay. All right. Let's do an example with an atom that's not carbon or hydrogen. And so I already know what this molecule is going to look like, but let's say here. So you're not going to be asked to go from here to here necessarily, more so depicting between, knowing how to depict between these, the structural condensed and the stick models. All right. So how would I depict this in a stick model? So I would have, make sure I had 4 points. 1, 2, 3, 4. Now here's a little bit the tricky part. I'll then use one more line and put the OH. Now this point does not represent a carbon. This is showing the bond between this final carbon and the oxygen. That's the one tricky part. That used to trip me up when I took organic chemistry. So just to recount our carbons here, this is carbon 1. Oops. 1, 2, 3, 4. And this is an oxygen atom. And then there's implied hydrogens here. There'd be 2 here, 2 here, 2 here. There's no implied hydrogens here because, again, this is an oxygen atom. So when we do this shorthand, I am so sorry that I just erased that all. So when we do this shorthand for organic molecules, we basically assume the carbons and the hydrogens, but heteroatoms, which are atoms that aren't carbon or hydrogen, so such as this oxygen, have to be depicted. They're depicted that you have to write them out, and whatever atoms are then attached to it. So there was a hydrogen connected to that. So one final example here, C4. This time I have a double bond between these 2 carbons. So how does that look in the stick model? So 1 point for each carbon, 1, 2, 3, 4. Implied hydrogens. But I add a second line here to depict my double bond. Condensed formula, which I just realized we forgot to do up here. So this was CH3, CH2. So here's the CH3 group, CH2. Here's another CH2, CH2, and then OH. So for this group, CH3, this only has one implied hydrogen because, let me use the highlighter, because there's, on this carbon atom, there's one bond here, one bond here, and one bond here. So that only leaves one space open for an implied hydrogen. So it's just CH. And the same goes for that carbon, CH, and then 3 implied hydrogens here, CH3. So here I just put a little table. So we went over some of these atoms, but we didn't go over rings, which I'll introduce here in a second. So rings work the same way, where each point represents a carbon. So here there's 6 points. And I liked this table because it showed all the implied hydrogens and how, you know, we go from this expanded formula to this formula here. So triple bonds, I showed an example of a double bond, but triple bonds work the same way, where we'll just add another line. So if we had 4 carbons and the middle 2 had a triple bond, we'd add a line on top and bottom of that already existing bond. So your OWL question 3 asks you to match these expanded structures here with a condensed formula. So yours might look a little different, but I'll show you some tips and tricks here. So I'm just going to start looking at this top one. So I know it has to end in a CH3 group. This one has a CH3 group. This one has a CH3 group. CH3, CH3, CH3. So that didn't help me much. Next, it says it has a CH2. Okay, this one has a CH2. This does not, and neither does this one. CH2, no CH2. So I've got to narrow down a little. It then shows a C and 2 O's. Well, on this molecule, I have another CH2 group, whereas here, I do have a C bonded to 2 O's. And so, as we are recognizing by process of elimination here, that this molecule must match with this one. Oops, let me draw a straighter line. But let's continue out just so it ends in a CH3, which is represented there. So nice. So looking at the next one, starts with the CH3. We've already determined that all of them do start with CH3. It then shows an carbon bonded to an oxygen. So it could be this one or this one, because the next group is a carbon bonded to an oxygen. It then now shows a nitrogen bonded to a hydrogen. So there's no nitrogen here. so it must be this guy. And then it ends in a CH3, which this one also does. So looking at the next one, starts with CH3. We know that all of them start with CH3. It then shows a nitrogen with 2 hydrogens. So this next one is a carbon on this guy, so it can't be this one. This next one is a nitrogen connected to 2 hydrogens. Okay. So CH3, then it shows a C bonded to an H and maybe another O, which happens to be this one. And finally, CH3 group, CH3 group, CH2, 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 CH2 here, and then C bonded to 2 O's and an O bonded to a hydrogen. Okay. So take your time with those because those are not easy. It takes time to start recognizing how organic molecules are depicted. So I also threw in this example because it shows this like more bubbly form, which is this is more realistic and true to what this looks like in space. So here, blue atoms are carbons, red is oxygens, and white are hydrogens. Now, I don't know how they expect you to know that, but I've been around, so I've seen this. So I have a molecule with 1 oxygen in the center of 2 carbons that are double or that are have 3 hydrogens around them. So I recognize that as this one, a hydrogen surrounded by 2 carbons that have, I'm sorry, an oxygen surrounded by 2 carbons that have hydrogens around them. Now I recognize this as this molecule. So I have a carbon, an oxygen. I have this carbon also bonded to another oxygen here. This oxygen bonded to a hydrogen, and this carbon bonded to a hydrogen. Now I recognize this one as being this bottom. So I have carbon, carbon, carbon. So 4 carbons, 1, 2, 3, 4. And then they're all, I can't see all of the hydrogens, but I know there's a bunch of hydrogens attached here. And then finally, I recognize this molecule, this oxygen surrounded by 2 carbons on each side, as being this molecule. So just a little review, how would we depict these in the line models? So this molecule would look like this, where this is a carbon, and then showing it being bonded to this oxygen. I'm going to change colors here. This in a line model would look like oxygen bonded to a carbon, double bonded to another oxygen, and this bond is bonded to an OH. So this is my carbon here, double bonded to an oxygen, double bonded to, or singly bonded to another oxygen that's bonded to an H. This guy would look like 1, 2, 3, 4, with all implied hydrogens. And this last one looks like 1, 2, bonded to an oxygen, 1, 2. So here's this carbon, here, here, the oxygen atom, carbon, carbon, with all implied hydrogens. So not that you necessarily need to know that for that problem, but I just wanted you to start getting familiar with that format. So next, looking at how these molecules bond, I'm going to tell you that this slide is not important for the exam, but this is there is an OWL question that does ask about these groups. So we're just make a table just real quick, just so you can get through the OWL question. So when carbon utilizes all 4 bonds for 4 different atoms, so such as this, maybe he's bonded to another carbon or something. This is an sp3 hybridization. And this is also known as an alkane. And so, you know, what this might look like molecularly is just single bonds everywhere. When carbon utilizes the 4 bonds, but for 3 atoms, so let's say hydrogen, hydrogen, and he double bonds to another carbon. This is sp2 hybridization. And the name for this is an alkene. So what this looks like here's my double bonds. Right? So this utilizes double bonds. When carbon utilizes all the 4 bonds, but only for 2 atoms, such as in a case like this is sp hybridized. Oh, I drew this wrong. So, sorry, 4 bonds, but only to 2 different atoms. This is sp hybridized. And this is also known as an alkane, which is associated with a triple bond. And so what this looks like in space here is a triple bond. So looking at our question 13, in which you need to know this, I already have the correct answer filled in here, but for this molecule, there's all single bonds. And so this molecule is an alkane because of the single bonds. And single bonds utilize sp3 hybridization. So this drop-down menu says like sp, sp2, or sp3. All right, so that's the only time you'll really need to know that. So I kind of showed an example of a ring earlier, but you're probably freaking out. You're like, oh my gosh, rings, like carbon chain, like, wow, okay, it just got more complicated. Well, yes, unfortunately. So sometimes carbons prefer to form a ring over the line by line structure, and that is because it's more energetically favorable. In rings, the points still represents carbons, and there are still implied hydrogens. So I like this diagram here because it shows you the implied hydrogens. And then it shows you without the implied hydrogens. So each point still represents a carbon. So the next problem I want to kind of demo here is OWL question 4. But I'm going to go ahead and we're going to look in OWL for this actual question because I want to be able to manipulate the image here. So this is not the same one I had screenshotted earlier, but I wanted to show you. So this little model tool here, you can manipulate by grabbing, holding down your mouse and rotating it. So for me, it makes a little bit more sense like that. And so here I can see all the single bonds. And then there's another carbon here. So this question is asking you to represent, based off this picture, how is this represented? Oops. Oh gosh, it zooms in. Okay. Crap. Okay. So looking here at my answer choices, these two look pretty similar. Only, this one's rotated. So I would say that this also represents the molecule shown. This also looks pretty similar here, only it has drawn out all those implied hydrogens. So this also represents my molecule. None of the rest, this isn't even a ring. And this has too many points and no line coming off of it, so it doesn't depict my molecule. The same with this, it doesn't depict my molecule. So I just wanted to show you an OWL how you can move those models there. So moving forward, organic chemistry utilizes functional groups. So yes, organic molecules are mostly made up of carbon and hydrogens, but there are these common groups that attach to these molecules. And so here, right, this is just carbon and hydrogens. And this is an example of a functional group. So here's a table of functional groups that you need to become familiar with. So in this module, we're going to be talking about alkanes, alkenes, alkynes, alcohols, ethers, alkyl halides. So I want to add one more functional group to this list. So anytime a squiggly line is represented, that just represents the rest of the molecule. So like in the picture I showed you earlier, I could depict this like this would just say, here's the alcohol functional group, and anything else could be attached, basically. That's what the squiggly line is showing. So I want to, like I said, I want to add one more to this group. Isopropanol. Which looks like this. So like I said, in this module, we'll be talking about alkanes, alkenes, alkynes, alcohols, and ethers. So alkanes are single bonded, right? We already used this term before. So just single bonded carbon and hydrogens. An alkene is when we have a double bonded carbon, again with a bunch of hydrogens. Alkane is a triple bonded carbon. An alcohol is when we have carbon attached to an O, which is directly attached to an H. And an ether is when we have carbon sandwiching an oxygen. So for your Al question 1, you're identifying functional groups. So some of these we'll talk about next week, but they are on that chart back here. So here's an example of an alcohol. It's a carbon attached to an oxygen that's then attached to a hydrogen. Alcohol. This is an amine. It's when a carbon is attached to a nitrogen, which is then attached to 2 hydrogens. This is an example of a carboxylic acid, when a carbon is doubly bonded to an oxygen, then singly bonded to an OH. This is an example of an aldehyde. It's when a carbon is attached to an oxygen and then attached to a hydrogen. This is a ketone. It's when a carbon is double bonded to a oxygen, but unlike in the aldehyde case, it's that carbon is then connected to 2 other carbons. So use that table on the previous page to fill in your corresponding Al questions, because you might not have the exact same molecules. So next I wanted to talk about the term hydrocarbons. So what are hydrocarbons? Hydrocarbons are groups or regions that are made up solely of carbons and hydrogens. So when I showed this molecule earlier, we could say that this area was the alkane region. Well, you could also call that a hydrocarbon. And this was the alcohol region. And so hydrocarbons are a bigger subclass of alkanes, which were singly bonded carbons, alkenes, which were doubly bonded carbons, alkanes, alkenes, alkynes, which are triply bonded carbons. There's also aromatics, which are rings in which every other side has a double bond. And so there's 2 different types of hydrocarbons, saturated and non-saturated, or sometimes called unsaturated. So it's saturated is only when you have single bonds. And so you can think of it being saturated because it has the maximum amount of carbons that it could have. The carbon is attached to the maximum amount of hydrogens that it could have. Whereas unsaturated is when it doesn't have the maximum amount of carbons. It basically has double or single bonds. I'm sorry, maximum amount of hydrogens. So alkanes are an example of saturated hydrocarbons, where alkenes, alkynes, and aromatics are examples of unsaturated. So next I want to introduce the idea of isomers. So here's a little definition for you. What is an isomer? It's when each of these two it's when two or more compounds have the same molecular formula, but different arrangements of atoms. And so both of these formulas, or both of these structures, have the formula C2H6O. But as you can see, they're arranged differently. And so we'll come back to this idea of isomers after we do the naming video, but I just wanted to introduce the idea of it. So next I have a little meme for you to remember alkanes, alkenes, alkynes. So I found this a long time ago when I was taking organic chemistry. I just thought it was cute because this is like printed on a t-shirt or something. But it's porcupine, he only has single bonds. Porcupine, he has double bonds. Porcupine has triple bonds. It's cute. Just a fun way to remember it. So the last question that I'm going to demonstrate in this first video here is OWL question 2. And so here we're classifying the hydrocarbons as alkane, alkene, alkyne, or arene, which is the same word as aromatic, which I had introduced as being a ring with every other bond being a double bond. So for my problem here, I have a triple bonded carbon. So this is an alkyne. Here I have two rings in which every other bond is a double bond. So this is an arene. Here I have all single bonds. So this is an alkane. And then lastly, I have double bonds. So this is an alkene. Okay, so the next video will be a little bit longer, but it will be about naming these guys. How do we name them? So a whole different naming system than the compounds, because now we have a lot of different carbons and a lot of different ways that we can arrange them.